I hope I'm audible and someone can just say yes or no or just yes. Okay, thanks, Priyesh. Thank you. So, once again, welcome back to week 6 of the problem solving session for the Introduction to Fluid Mechanics course. And once again, sorry for the delay. So this session was scheduled to be held on Tuesday of this week, but because of some unavoidable circumstances, I had to postpone this session. Nevertheless, still, I will try to cover up the concepts that were taught by Professor Chakraborty in this week's discussion, and hopefully, once I discuss the concepts as well as the problem that will be relevant to the assignments. I don't know whether the assignment solution will be released or not, but still you'll at least get a recapitulation of the topics that were taught by Professor Chakraborty, and moreover you get an idea to solve questions that will require relevant for your assignments if they have not been the answer have not yet been released, or otherwise they will also be quite relevant for your exam. Okay, so with that idea in mind, and moreover I think again similar to previous week, this week's topics are not that extensive, so I will try to cover up as much as I can from my end, but as per our regular agenda, I will just briefly go through them because all of them have been quite elaborately discussed by Professor Chakraborty. So I'll briefly go through them, go through the derivations, and hopefully help to recapitulate the concepts, and then we'll directly go to the questions so that you can try out the questions and tell me the answer, and then we can just go ahead with the session. Okay, so with that brief introduction, let's start. So in the previous week, we were discussing the continuity equation, or basically the mass conservation equation. We started our discussion with the fluid kinematics, where we were introduced to one of the major conservation laws, that was the mass conservation, and we were able to look into the into the differential form of the continuity equation. So so that was basically written as let me just write it in a differential form. It was basically written as dou rho by dou t plus nebula dot rho v equal to 0. So this is in differential form of the continuity equation. Or mass conservation. Just 1 second. So moreover, and now we would like to look into the equivalent form of the governing equation of the continuity equation in an integral form. Why integral form? So one of the key things to notice that these conservation laws that we are looking into, say the mass conservation or the momentum conservation, are in terms of the control volume. Okay, and since we are looking into a control volume and looking into a bulk property of the fluid over a definite area, then the governing equations that we are eventually going to derive would be valid for a definite control volume, which would indeed comprise of a volume integral. Okay, so sorry. Thanks for letting me know, but I have let everyone in who are trying to join the meeting. So that you can see in the screen. So whoever would like to join, I will just admit them. So right now there are no people in the queue, so I think I have admitted every one of them. But hope it's okay. Yeah. So as I okay, see. So now the okay. So as I was mentioning, yeah. So the governing equations that are inherently derived from the control volume approach would include a volume integral, and thus will be primarily in the volume integral form. Then we, as one of the students were asking in the last class, that we need to apply the Gauss divergence theorem to convert the surface integrals to a volume integral, and then find a net equivalent differential form of that governing equation that we'll eventually see when we discuss the Reynolds transport theorem. Okay, so that's why the concept of a differential form of the governing equation as well as the integral form of the governing equation comes into picture. And depending on the problem in our hand, these two forms of equation may become relevant according to the need of the problem. Okay, so which we'll eventually see. So now we, just for a as a precursor or a brief overview of these two different types of forms of governing equations, we just discuss about the just one second, sorry for the disturbance, just 1 second. Okay, sorry for the disturbance from my end. Yeah, sorry. So as I was mentioning, depending on the type of problem, these do different forms of the governing equation will become relevant. Okay, so let's look into the uh, equivalent integral form of the mass conservation equation. So let us consider a very simple situation. There is a 1D steady flow. Okay, a 1D steady flow basically mean that the Cartesian coordinate or the coordinates that we are dealing with will only be a single coordinate. So in this case, say let it be the x coordinate, and steady flow would mean that the time derivative or the local acceleration component would be 0. Okay, I will not say specifically acceleration, I will just say that the local time derivative would be 0. So this term would be equal to 0 for a steady flow case. Then we are only left with this term, which is shown by this in the case of a single dimensional system, the one dimensional system. Then we carry forward an integral of this particular term over a particular elemental volume. Then we can write this integral, and of course this will be equal to 0 because the integrand that we initially chose was 0. So this integration will also be 0 for any arbitrary volume. Okay, then we can again generalize it a bit further. So we can write this in the form of this, where this inverse triangle or delta is the nabla operator, and we are doing a dot product between this nabla operator over rho u I cap, where rho u I cap denotes the component of the I could say the mass flow rate in the I cap direction, okay, or in the x direction. Okay, so it's just a generalized form. We are doing it so that we can apply the Gauss divergence theorem, because Gauss divergence theorem is only applicable. It's only applicable over a vector field. So we need to have our function over which this divergence operator operates to be a vector. So we need to convert it in the equivalent vector form so that we can apply the Gauss divergence theorem. So this is the doubt that one of the students were asking, what's the Gauss divergence theorem. So it's basically a transformation from a volume integral to a surface integral. Of course, this kind of conversion between line integrals to volume integrals, or line integrals to surface integrals, or conversion of volume integrals to line integrals, or vice versa, or conversion of surface integrals to line integrals and vice versa, are thoroughly discussed in the vector calculus part of first year mathematics. So I don't think I will need to go through that thoroughly. And of course it's a good exercise if you can just go back and go through those theorems. So they are basically the The Stokes theorem, the Stokes theorem, the Gauss divergence theorem, Gauss divergence theorem, and the Green's theorem. And Green's theorem is basically a special case of the Stokes theorem, but you can then also most of the books tend to mention it separately, so you can go through this Green's theorem as well. Okay, so once you go through these examples and see how the conversion between these different types of integrals are done and why they are done, you will appreciate the use of these theorems in the fluid mechanics context. Okay, so given that brief overview, so we need to apply now a a Gauss divergence theorem, basically to convert this volume integral to a surface integral. So the functional form of the Gauss divergence theorem is given by this, where the volume integral of nebula dot f, or the divergence of f, where f is a vector field, is converted to a surface integral where f remains the same, that is the vector field over which we are operating, and it is dot product with the normal vector to the area over which we are integrating. Okay, and this area is basically the area engulfing this control volume. Okay, so this is the conversion between the volume integral to the surface integral and vice versa. Okay, and this is something that we'll eventually do when we are deriving the different forms of mass conservation and momentum conservation using the Reynolds transport theorem. Okay, so for our case, as I mentioned, this f, the vector field, was rho u I cap, so we just need to substitute f as rho u I cap in these two equations to get delta dot rho u I cap dv is equal to the surface integral of rho u I cap dot n cap dn. Okay, and in this case I'm sorry, this rho u I cap dot n cap, for a simple flow, I think I forgot to draw the diagram here. So it was basically something like a nozzle where the flow was from this to this, right? Something like this. I forgot the diagram specifically. It was a very simple 1D flow. So in this case, this is the inlet, okay, and this is the outlet, and say the volume of this particular shape would be V, and the area, say this would be AI, and this would be AE. Okay, AI corresponding to the inlet area and AE corresponding to the outlet area. And here you can see that at the inlet, it would basically, the n cap will basically be the negative of the I cap vector, so we have substituted it by here, substitute it by this here, and I'm sorry, and in the outlet, the n cap will correspond to, okay, I'm sorry for this noise, okay, and this, at the outlet, this n cap will correspond to the positive I cap, because the flow direction of the flow and the normal area vector are along the same direction, so it will be positive here. So once you do that, you will see that this is basically negative of this, so this can be taken in the right hand side or vice versa. Then we'll get something like the surface integral of rho u dA, where the area is integrated over AI, and is equal to rho u dA, where it is integrated over AE depending on the area. Okay, so this equation basically corresponds to the fact that for a steady state, the mass flow rate through AI must be equal to the mass flow rate through AE. Okay, and again, a much more simplified form of this equation can again be written as rho I AI UI bar is equal to rho E AE UE bar, where rho I denotes the density at the inlet, AI denotes the area at the inlet, UI denotes the average velocity at the inlet, and correspondingly rho E denotes the density at the outlet, A denotes the density of area at the outlet, and UE denotes the average velocity at the outlet. Okay, and we'll see how we can get the concept of this average velocity. Okay, so given that the density does not vary over a given section, we can simplify this integral even further. So we can take now the density out of the integral. So rho I is over integral over UdA over AI. So it becomes rho I ui bar AI. Okay, where this ui bar can simply be written as, or u bar can simply be written as the integral of UdA over A. Okay, because these two densities can be cancelled out, so the average velocity u bar can be written as integral of UdA over A. Okay, and for a constant density, for example, for a constant density in this equation, we can cancel out density from both the sides because rho I would be equal to rho E. Basically, we are saying that the flow is incompressible. So you can, or I will not say incompressible specifically. I will say the density is constant because we saw that even if the density varies, the flow can be incompressible when we are dealing with the differential from the governing equation. So you can go back and check it. So I will not say the flow is incompressible because it's a more generalized case. So I will say the flow is incompressible with density being constant. So in that case, we can take out or cancel out these densities from both the sides. So we will be left with AIUI is equal to AUE. So this equation basically tells that the mass flow rate at inlet is equal to the mass flow rate at the outlet, and given that the density can be considered constant, we can say that the mass conservation basically boils down to this form of the equation, where we can say that the volume flow rate at the inlet is equal to the volume flow rate at the outlet. Okay, because volume flow rate, or which is popularly denoted as Q, is basically the product of the area times the velocity of the fluid, okay, that passes through a particular cross-sectional area, where this is denoted by A. Okay, so I hope it is clear till now. Okay, so let us now look into an example. Okay, it's a small example that was taken by Prof. Chakraborty in the class. So again, the beauty of the example taken by Prof. Chakraborty is that it's one of the more complicated examples or problems that can be discussed in this context, at least in this topic, and Prof. Chakraborty very elegantly takes this example and solves it very beautifully and in a much simplified manner, because of which many of the concepts that we want to convey are being clarified through this problem. Okay, but once again, this problem is not something that I am writing on my own. It's something that was discovered by Prof. Chakraborty himself very elaborately. So if I'm not able to clarify it properly, you can just go back to the lectures, or you can ask me right here as well. But then if I'm not able to clarify it even properly even after that, you can just go back to the lectures. Okay, so it's basically a scenario where there is a plate that is being fixed, that is being placed at a particular height from the surface. The height at which the plate is being placed is h, and there is a mass flow rate through the bottom surface, where the bottom surface is porous. Okay, again the concept of porosity comes here, where again this in itself is a very elaborate subject to read or to discuss, and then it can be extensively studied separately as a separate subject or a sub-subject of subtopic of fluid mechanics. But then also it's good if you are introduced to it. Okay, so in this case basically means that there are some holes through which fluid flow passes through it, and they can be modeled as having a particular average velocity denoted as V0. Okay, so V0 would basically mean that the velocity profile basically shows that the velocity is constant through this particular cross-sectional area. Okay, so the inlet velocity is V0, and the fluid flow after coming through this porous media or through these pores, it strikes this stationary plate and is deflected outwards from both the sides of the geometry. Okay, so it is being deflected out from both sides of the geometry, and here what happens is that now again we are introduced with the concept of boundary conditions. Okay, so we discuss it elaborately when we are solving some specific cases of the Navier-Stokes equation. But right now, boundary conditions will basically mean that what is the value of these velocities or pressure at some particular boundaries of the geometry. So you will see that at this solid surface, there is the bottom surface of this stationary plate, the fluid flow cannot pass through this surface, right? Because it's not porous, it's a solid surface. So we can say that the velocity at this point or at this edge of the plate would be 0. Basically, the y component of velocity at least at this point would be 0 because the flow cannot penetrate through this plate, and that's why we term this particular boundary condition as the no penetration boundary condition. Okay, we will also deal with no slip boundary conditions when we are discussing with viscosity, but since in this case we are not inherently saying that the flow is viscous, so we are not introducing you with the concept of no slip boundary conditions, but this is something that we have briefly introduced in the first lecture about the no slip boundary conditions, how the no slip boundary conditions comes in picture, but we are not applying it here because we are not inherently saying that the flow is viscous, the fluid is viscous. Okay, so the viscosity can be neglected in this particular case. So the question is, given this scenario and of course the geometry, find the expression for the x component of velocity and the y component of velocity, and correspondingly find the acceleration. Okay, so here in this case we have the inlet velocity as v naught, the geometry is as the length of the plate being L and the plate being placed at a height of h and the width of this plate being equal to b. Okay, so these are the things that are already given, and it's given that the flow is a steady flow with constant density. Okay, so these terms are very crucial to simplify our understanding, because initially we might start with the same governing equation that we discussed, that is because this is a governing equation that we have in our hand right now. Okay, but the thing is, since it is already told that it is a steady flow with a constant density, then we can again simplify this equation even further, and so we can see that it's much more simpler to deal with the integral from the governing equation in this particular case, because since the flow is inviscid, okay, since the flow is inviscid, so we can just treat the velocity to be constant throughout the cross-sectional area. Okay, so that's why you can write the continuity equation simply as ai ui bar is equal to ae ue bar. Okay, I think you understood why we wrote it. Okay, because like I just discussed this entire derivation, so keeping into consideration that the flow is steady and of constant density, and given that the flow is inviscid, we can simply write the governing equation as aiui bar is equal to aue bar. Okay, and now we need to substitute the values of aiui bar and ae and ue bar. Okay, and ue bar is something that we need to find because we do not know the expression for ue at the exit, but we know the expression for the inlet velocity. It is given by v naught. Okay, so ai would be bx, basically the length up to which the flow is incoming through the inlet, and ui is v naught because it's a constant velocity as given in the question. Similarly, at the outlet, ae would be equal to bh because the area remains constant at the outlet, so it would be b times h, and u is something that we need to find, so you can just write it something as a function of x. Okay, x or y, you can write something like that. You will eventually see that this is only a function of x. Okay, so once you substitute these values here, simplifying it, you will get that uex is equal to v naught x by h. Okay, and you will see that since v naught and h are constant and only variable is x, so ue is only a function of x, so we can write ue as u of x only. Okay, so it will imply that the derivative of dou u by dou y is equal to 0. Like if anywhere it comes into picture, then dou u by dou y will be equal to 0. Then from the continuity equation in the differential form, again we need to go back to the differential from the equation, because the continuity equation gives a relationship between the two components of velocity. Okay, so that's the only equation that we have in our hand right now to find the expression for the v component or the y component of velocity. So we need to again take 8 of the differential from the governing equation. So we again go back to the differential from the governing equation given by dou by dou x of rho u plus dou by dou y of rho v equal to 0. Again the temporal term is neglected because the flow is steady. Again, since rho is constant, so density can be taken out of this equation, so we can write dou u by dou x is plus dou v by dou y equal to 0. Now u is given by v naught x by h, so dou u by dou x would simply be v naught by h. Okay, such simple substitution of u by v naught x by h. So we can write v naught by h plus dou v by dou y equal to 0. Now we can write something like it's something as dou v by dou y is equal to minus v naught by h. Okay, now to find the expression for v, we need to integrate this equation again. This is a partial derivative, so we need to accordingly take the constant of integrations very carefully. Okay, so once we integrate it, we will get something like v is equal to v naught y plus h plus some function of x. Why? Because if we take this, the derivative of this with respect to x, with respect to y, the only term that will be left is this term v naught by h, but this term will also be 0 because it's independent of y, so the partial derivative of this with respect to y would be 0. That's why we take the consider some function of x. Okay, and now to find this the functional value of f of x, we need to take the aid of the boundary conditions that I initially introduced. Okay, so we have only one boundary condition right now, or since there's one constant of integration that we need to find, so we can take aid of the one of the boundary conditions that we know, that is at y equal to h. If I go back to the diagram, at y equal to h, the y component velocity, this v is 0 because there is no flow across this particular plate. That's why you can write at y equal to h, v equal to 0 from the no penetration boundary condition. And once you substitute this value of y here, y is h here, it will become minus v naught, and this will be 0, so 0 would be equal to minus v naught plus some function of x, or f of x is equal to v naught. And once you substitute the value of f of x in this expression, we'll get v as v naught 1 minus y by h. Okay, and now you got the value of both v and let me go back, u. So from that you can easily find the expression for acceleration. So ax would be given by dou u by dou t plus u dou u by dou x plus v dou u by dou y. I hope by now you have remembered how to find the expression of acceleration. So I don't think we need to reiterate it again and again. So you can see that this term would be 0 because the flow is steady. So ax would be given by u dou u by dou x plus v dou u by dou y. So dou u by dou y, as we saw, that is 0 because u is only a function of x. So this would be 0, and we will be left with u dou u by dou x. So must substitute the value of u in this expression, so we'll get ax as v naught square x by h square. Similarly, ay would be given as u dou v by dou x, u dou v by dou x plus v dou v by dou y. And again, dou v by dou x is 0 because v is only a function of y, from we can see from here. So just the second term is left, so ay would be v naught 1 minus y by h times minus v naught by h. So it will finally give us ay is equal to minus v naught square by h multiplied by 1 minus y by h. Okay, so I'm sorry. So once you know both of these, you can write as ax ik plus ay jk. Okay, just substitute these here, but it's just an extended work, so we can just avoid it, or you can write it depending on your choice. So one interesting thing to note here is that here, even though the velocity components are not functions of time, we get an acceleration. So why? Because we initially saw that the acceleration is composed of both local acceleration and convective acceleration. So the acceleration that we are getting here is because of the convective part, because even if the velocity components are independent of time, they are varying with space, and this spatial acceleration or the convective acceleration part is what that contributes to net acceleration of the fluid flow through this particular geometry. Okay, so with that discussion, let us now look into the second part of the deformation of fluid element, because in the previous lectures we discussed about the linear deformation of the fluid element, and now we again introduce you to the angular deformation of the fluid element. Okay, so in order to save time, I have just skipped the diagram that Prof. Chakraborty had initially drawn. So he drew something like a rectangle and saw some line elements of the fluid, elements of the particular fluid molecule. And he derived this expression that is basically finding the average of the angular deformation of the fluid element. So I am just skipping those derivations. Again, you will eventually end up with these terms only, so I am just skipping that part in order to save time. But I'm again reiterating, uh, going back to those derivations, if you have taken notes, is a good exercise, because you will get an idea of how you are able to obtain these expressions from the angular deformations of the line elements. Okay, so with that idea you can go back to the derivation to confirm these expressions, but for now I will just skip that part and directly come to the uh, final form of the expression that Professor Chakraborty derives. Okay, so the angular deformation of fluid element is basically the rate of I'm sorry, rate of change of angle between the two line elements in the fluids which were originally perpendicular to each other. Okay, so skipping the extensive derivation, we can conclude that for the Cartesian coordinate system, because Professor Chakraborty also derives it for the Cartesian coordinate system because it's the most simplified case, so we can write something like epsilon dot xy is given by dou v by dou x plus dou u by dou y. So it's very easy to remember. It will simply be, you need to exchange the velocity components for the derivative that you are taking. So if you are taking derivative with respect to x, just take it derivative just replace the velocity component with the other coordinates. Okay, so it will be, for x you need to replace by v, and for y you replace by u. Okay, so you are now you are done with epsilon dot xy. Similarly for epsilon dot yz, for derivative with respect to y, you need to take the other velocity component, so it will be w, so it will be dou w by dou y. Similarly, it will be dou v by dou z. Finally, epsilon dot zx would be, for z you need to deal with the other component, that is u, and for x you need to deal with w. Okay, so it will be dou u by dou z plus dou w by dou x. Okay, or in general, in index notation, epsilon dot ij would be written as dou uy by dou xj plus dou uj plus dou xi. Okay, and you will see that this is basically a second order tensor, because you are dealing with two free indices. Again, to just, if you are new with the tensor notation, it's not that extensively discussed in this course. We will discuss it briefly in this part, and then for the derivation of the momentum equation in the later part of the course. But for now, we can just go back to the first week. Okay, first week discussion, to get an idea of what you mean by the tensor notation, what are the free indices and the repeated indices or dummy index. So you can recollect that. For now you can see that there are two free indices, because none of them are repeating, so it's a second order tensor. Okay, and it is written as dou u by dou xj plus dou uj by dou xi. Okay, so one key thing to note here is that sometimes the expression for epsilon dot ij is varies from author to author, but in general, I'll just write it here. It is sometimes, it's most of the time, most of the standard textbooks, it is written something like half of dou ui by dou xj plus dou uj by dou xi. Okay, this half factor is basically taken into picture in order to accommodate the factor of 2 when we write the Newton's law of viscosity in the index notation. Okay, so this is the Newton's law of viscosity in the index notation. So these 2 and this half will cancel out, so we will only left with mu epsilon dot ij. Okay, and in some textbooks what happens is that rather than writing as 2 mu epsilon dot ij, sometimes they write it as mu epsilon dot ij, where the factor of this 2 is accommodated here, so we can write epsilon dot ij as dou ui dou xj plus dou uj plus dou xi. But for this particular course, or for this particular problem session that I am going to take, I will preferably use this form, because this is the one that we will eventually see when we will be discussing the Reynolds transport theorem part. So in order to be in line with the discussions, I would like to keep this notation intact. So epsilon dot ij you can write as half of dou ui by dou xj plus dou uj plus dou xi. Okay, so and in order to help you out to see that it's a second order tensor, I have just decomposed it in the Cartesian coordinate system. So epsilon dot ij is in the full tensor notation form is written as this one. Okay, and you will see that this is symmetric tensor. Why? You can see that uh, these two components are identical. Okay, and these components are identical, and these components are identical. So basically, if you invert it, okay, if you invert it, I'm not, no, sorry, I'm not saying invert it. If you take a transpose of this particular matrix in basically it's a tensor, but if you just take the transpose of this particular tensor, you get the same one. Okay, so or in other words, if you just substitute the value of j and I or interchange them, you will end up with the same expression. So that's why it's known as a symmetric tensor. Okay, I hope it is clear till now. Okay, so let's I hope the notation that I prefer is clear. So in order to be in line with the later part of the course, I would like to reiterate that the epsilon dot ij, which is basically the strain rate tensor, is half of dou ui by dou xj plus dou uj plus dou xi. Okay, I hope it is clear. Okay. Then comes the concept of angular velocities. Again, basically the arithmetic mean of the angular velocities of two line elements that were originally perpendicular to each other. And once you derive it, as it was done by Prof. Chakraborty, so we find that it is denoted as omega ij. So it is written as half of dou ui by dou xj minus dou uj by dou xi. Okay, it's similar to epsilon dot ij, but it's just replaced by minus sign here. Okay, and you will see that this is again a second order tensor because it is dealing with two different indices, free indices. So it's again a second order tensor, and the interesting thing to note is that it is a skew symmetric tensor. Okay, so if you write the, now I'm not saying about this particular tensor, but if you write the angular velocity tensor here, you will see that all of its diagonal elements would be 0, and if you take transpose of this particular tensor, you will see that it's a negative of the original tensor. Okay, that's why it is written as omega ij is equal to minus of omega j. That's why it says skew symmetric tensor. Okay, and if you recollect the basic concepts of matrix algebra, you see that any matrix can be written as a sum of a symmetric and a skew symmetric matrix. So you can apply a similar concept here, where a general velocity gradient, it is dou u by dou xj, can be represented as the sum of a symmetric tensor, that is the strain rate tensor, this is a symmetric tensor, and the sum of the angular velocity tensor, it is given by omega ij, which is a skew symmetric tensor. Okay, okay, so I hope it's clear. Now let us look into the vorticity. So vorticity is basically that is 2 times the angular velocity. Again, you will be dealing with a 2D tensor, second order tensor. So or in general sense, is the vorticity is denoted as omega is omega, so it's capital omega. So this is known as small omega, and this is known as a capital omega. Okay, so just to differentiate between these two types of vectors, so vorticity is denoted as omega. Okay, capital omega, and in some textbooks is also represented as small omega, and most of the times I will say that most of the textbooks don't really differentiate between this angular velocity tensor and vorticity tensor, because more or less they give you a same idea. Basically it tells you about the rotationality of the fluid elements. So most of them they denote the same thing, because you'll see that the only thing that differentiates them is a factor of 2, which is insignificant in the case of fluid mechanics, because we'll mostly be dealing with the order of magnitudes of these different terms. But just to show you the difference, that there is a difference between these two things, basically a factor of 2, and we are just denoting it here. Okay, so it's basically the curl of the velocity field. Okay, what is basically the curl of the velocity field, which will again give you a second order tensor, which is 2 times the angular velocity. Okay, so now we come to a very important concept, that is the concept of stream function. Okay, So stream function, I would say, is basically a simplification, is a function that is used to simplify the governing equations. Okay, so you'll see that this stream function is only applicable, it's very very important to know, and I will reiterate again and again. The stream function is only applicable for a 2D incompressible flow. Okay, or and most you have to, and more importantly, if you want to give more emphasis, it is the 2D case. So stream function is only applicable for 2D geometries, okay, or 2D fluid flows, because there is a relationship between two velocity components from the same function which satisfies the continuity equation. Okay, how you will see. So here we define u as dou psi by dou y and v as minus dou psi by dou x. Now if you substitute this in this continuity equation, you will see that, let me write it, dou by dou x, u is dou psi by dou y, right, plus dou by dou y, v is minus dou psi by dou x, right. Then you will see that it is dou square psi by dou x dou y minus dou square psi by dou y dou x. And if we consider psi to be a smooth function, which is basically been represented here as a continuously differentiable function up to second order, because we need to differentiate it 2 times, so it has to be continuously differentiable. And if it is continuously differentiable, basically if it is smooth function, then the order of differentiation is not that significant. So with that idea in mind, we will see that this term is equal to 0. So we will see that the definition of u in terms of psi inherently satisfies the continuity equation. Okay, so that's why it's only applicable for 2D incompressible flows. So it's not, now we are not discussing about steady or unsteady. It can be again be applicable for unsteady flows as well. You have to define the equation accordingly. But if you are dealing with 2D incompressible flows, then the governing equation or the mass conservation equation reduces to this form, and once you substitute it in this form, then you get u as dou psi by dou y plus v is equal to dou psi by dou x. Okay, so this is the formal definition of the stream function. Okay, then now again, if we just consider psi as a function of x and y, because it's only valid for 2D flows, so it will be a function of x and y only, is in a Cartesian coordinate system, then d psi, that is the complete derivative of psi, would be dou psi by dou x dx plus dou psi by dou y dy. So I think this part of finding the complete differential of a particular function I have discussed thoroughly in the previous lectures, so I will not go to it again and again. And once you substitute the value of dou psi by dou x and dou psi by dou y, so dou psi by dou y is minus v and dou psi by dou y is u from this expression, so we get dou psi as minus v dx plus u dy. So for d psi equal to 0, you will have v dx minus u dy equal to 0, or dx by u is equal to dy by v, and you will see that this form of equation is quite familiar, which is basically the equation of streamline. Okay, and it basically tells us that the stream function psi is constant along a streamline. Okay, for psi equal to constant, it basically is a streamline. Okay, so 2 things to note, again very important points to note. The stream function psi is only defined for 2D incompressible flow. Okay, but the streamlines are defined for all types of flows. Okay, while we are discussing about streamlines, there was no underlying specification that we mentioned regarding in what cases we can define streamline. It was basically told it's the instantaneous fluid visualization technique, where which tells us the velocity of the, where the tangent along the streamlines tells us the velocity at that particular point. Okay, instantaneous velocity at that particular point. So there was no underlying specifications that were mentioned while defining the streamlines, so it is applicable for all types of flows. Okay, and there was again one extensive derivation that were conducted by Prof. Chakraborty, which concluded that Q2 minus Q1 by B, it basically showed that the mass flow rate between two streamlines can be given by this expression, and it tells that if psi1 is equal to psi2, then q12 will be equal to 0. Like if you have psi1 equal to psi2, then this term would be equal to 0. So we'll have the net mass volume flow rate is equal to 0. So it basically tells us that there is no flow across a streamline. Okay, I'm sorry that if I'm not able to, like, if you're not able to understand this expression. So actually you can just go back to the lectures where the extensive derivation has been done to conclude this. But I just wanted to come to important fact or important point that there is no flow across a streamline. Okay, it's again a very crucial property of a streamlines for you to know. That's why I wanted to go back to this derivation. But for more clarification, you can go back to the lectures where this derivation was thoroughly done. Okay. Now then again we come into for the final topics of discussion for this for today's session. That is the concept of velocity potential. Okay, so similar to streamline, there is another function that is extensively used to simplify our understanding of fluid mechanics. That is the concept of velocity potential. Okay, so let me go back to the stream functions. So if I go back here, you may initially ask, like, sir, we already know about u and v, then why deal with psi? Okay, why deal with the stream function? So here you can see that if you are able to define a stream functions for this particular fluid flow, okay, then you will see that the only variable that you need to derive or they need to find out is the stream function. So once you know the stream function, you can easily find out the velocity components, and again you can easily then deal with different kinds of scenarios. Okay, and if you are again dealing with the momentum equation, then from the stream function itself you can find the expression for pressure. Okay, we'll eventually see when we deal with the momentum equation. But the thing is that you are able to reduce the number of variables that you need to evaluate. Okay, so initially you had to find out u and v separately, but if you are able to define a stream function, you only need to find the expression for psi, which will eventually give you the expression for u and v. Okay, but again the limitation was that is only valid for cases where the flow is 2D and incompressible. Okay, and again you know that this kind of flows are again very rare or very idealized, or can only be obtained in idealized cases. Okay, but still this gives a very good idea of the physics of the flow, and on that you can build up your concepts, and then again once you know the basics, then you can apply it on the different difficult geometry, difficult scenarios. Similar to this, again we have the concept of velocity potential, which is again follows the same idea, but it is only applicable for irrotational flows. Okay, again I'm saying, again the specific case for the definition or the validity of velocity potential is that it's only defined for irrotational flows. Okay, stream function is valid only for 2D incompressible flows, and velocity potential is only valid for irrotational flows. So there is no limitation for the flow to be 2D. Okay, so this is not required. Okay, flow being 2D is not required. And moreover, you can see that it is very easily defined for the three velocity components separately. Okay, so you can see that now, since del cross v equal to 0, because the flow is irrotational, you can define a conservative flow field as v being the gradient of a particular scalar function, that is psi here. Okay, so u can be represented as phi here. So u is represented as dou phi by dou x, v is represented as dou phi by dou y, and w is denoted as dou phi by dou z. So you'll see that this definition basically comes from the fact that if you, let me just try to derive it. Maybe say you're dealing with an irrotational flow. Okay, you're dealing with irrotational flow, and it will basically give you I cap, j cap, k cap, dou by dou x, dou by dou y. It is a very standard problem that comes into many fluid mechanics exams. So you need to find how you have come into this conclusion. Okay, so just take the cross product of nebula and v. So you will be left with I cap is dou w by dou y minus dou v by dou z. Okay, I'm just taking the cross product, nothing complicated. Then dou w by dou x minus dou u by dou z plus
k cap is dou v by dou x minus dou u by dou y. Okay, that's the cross product. So for this to be equal to 0, all these terms has to be individually equal to 0. Okay, so you will be left with dou w by dou y minus dou v by dou z has to be equal to 0. Dou w by dou x minus dou u by dou z has to be equal to 0, and dou v by dou x minus dou u by dou y has to be equal to 0. Okay, and you will see that if you are defining u, v and w as something like this, then this substitution inherently satisfies all these conditions. Okay, and it's from this understanding we are able to derive the expression for the or relationship between the velocity components and the velocity potential, which is phi. Okay, so once you got an idea of the definition for the stream function and the velocity potential, now let us consider a case where we will be dealing with a much more specific case, that is a 2D incompressible flow, and which is irrotational as well. Okay, so in this kind of scenario, the flow for this kind of flow, both the stream function and the velocity potential are defined. Okay, or it is valid. Okay, so now we will have that. Then for 2D case, d phi, that is basically the complete derivative of phi, can be represented as dou phi by dou x plus dou phi by dou y into dy. Okay, now dou phi by dou x is u and dou phi by dou y is v, so just substitute that, so you get d phi as u dx plus v dy. Okay, for a constant value of phi, d phi will equal to 0, so you will left with dy by dx for phi the constant is minus uiv. Okay, it's just simple algebra, so I'm skipping that part. Similarly, for stream functions, you will have that dou psi d psi is equal to v dx minus u dy, or for psi equal to constant, d psi equal to 0, or dy by dx for psi equal to constant is v by u. Okay, so you will see that if you take the product of these slopes, that is the slope of phi constant psi, you will see that it is equal to minus 1. So it basically tells us that the lines of constant stream functions and the lines of constant velocity potential are perpendicular to each other, except at the points where u and v are equal to 0, not equal to 0, because if u or v are equal to 0, then these two fractions will be undefined, so it is difficult to define the slope at those particular points. So except at the points where u and v are equal to 0, these lines of constant psi and constant phi are perpendicular to each other. Okay, so it and more popularly is also defined as something like the streamlines and the lines of constant potentials are perpendicular to each other in the flow field, except at the stagnation points. Okay, so now we have that u is dou phi by dou x and v is dou phi by dou y. So from the continuity equation, we will have that dou u by dou x plus dou v by dou y equal to 0. So if we substitute the value of u and v in this case, we will have dou square phi plus dou x square plus dou square phi by dou y square is equal to 0. And this form of equation is also a very popular form of equation in the field of mathematics, which is known as the Laplacian, because dou square by dou x square plus dou square by dou y square, this form is known as the Laplacian operator. So the Laplacian of the phi is equal to 0 in the case of 2D incompressible and irrotational flow. Similarly, for in the case of stream functions, u is dou psi by dou y and v is minus dou psi by dou x. Then for irrotationality, we have dou u by dou y minus dou u by dou x equal to 0. This is the basic relationship between these two components in terms of the angular velocity. Then if you substitute the value of u and v here, we will get that dou square psi by dou x square plus dou square psi by dou y square is equal to 0, or basically nebula square psi is equal to 0, or the Laplacian of psi is equal to 0. So we will see that both of these equations satisfy the Laplacian. So Laplace for a 2D incompressible irrotational flow, the velocity potential as well as the stream function satisfy the Laplace equation. Okay, and why this is important, or why this is crucial, because the solution of the Laplace equation is a very standard solution, so which can be easily found in the different texts, so that's why it's important. And basically in these cases, both psi and phi are known as harmonics. Okay, but the functional form of psi and phi will be different even if the boundary equations are same, because the boundary conditions corresponding to psi and phi would be different. Okay, so with I hope it's clear till now. It's something that I just reiterated that was discussed by Professor Chakraborty, but I hope I was able to make it a bit more clearer. But again, if there's any doubt, you can ask. Otherwise, I'll directly go to the questions. Okay. Is it fine? Should I go to the questions?
Sir, what are harmonic functions?
They are the functions that satisfy the Laplace equation.
Okay, sir.
Thank you. So let us go to the question and answers part. I think the solutions are already being released, but you can just consider it as a practice session. So let us go through it. Okay. So I hope the questions are visible. Okay. So let us look into the first question. So the first question is, which of the following statements is or are incorrect with regards to a forced vortex? Okay. So the thing is that I have not thoroughly discussed or exclusively discussed about forced vortex, but there was a discussion taken by Professor Chakraborty where he discussed one problem when related to forced vortex as well as free vortex when he was discussing about circulation. Okay, basically a closed line integral of the velocity component. Okay, so this circulation is basically defined as the closed line integral of the velocity component. Okay, so there he discussed about the force vortex and he discussed about different properties of force vortex. So if you have that in your notes, you can go back to it and just tell me which of the statements are incorrect regarding a forced vortex. Okay. Question number 1. I'll give you 2 minutes, then you can just, it's simple, but still you can try. B. Okay. So Saurabh says it's the only incorrect is B. So others, can you contribute? Okay, so I think it would be a good exercise if I went back to that question that was discussed by Professor Chakraborty. So that will give us a brief idea about force vortex and about also about the circulation. So that part I skipped because I thought that when we discuss this problem, those concepts will come automatically. Okay, so since it has done the same thing, so let us go back to the questions. Okay, so the force vortex is defined as something like V theta is equal to omega and Vr equal to 0. Okay. So since we are dealing with case where we are dealing with rotating flows, so it's just more suitable to define these kind of flows in terms of the cylindrical coordinate systems. Okay, so if you're dealing with uh, vortices, both free vortex or force vortices, force vortices, it's just much more suitable to define the velocity components in terms of the cylindrical coordinate systems. Okay, or polar coordinate system. Since it's 2D, so it's very difficult to differentiate. So you can just tell it's much more suitable to define them in the terms of polar coordinate system. So instead of having u, v, and w, we are having v, theta, and vr. Okay, where v theta basically denotes the tangential component of the velocity. This is basically the velocity. If you are dealing with something as this, like in this kind of scenarios, flows rotating, then the component of velocity along the tangent of the circle would be the tangential velocity component, and the component of velocity towards the center of the circle would be the radial velocity component. Okay. So in this case, in terms of force vortex, we'll have that the radial component of velocity is given omega r, where omega is the angular velocity and r is the radial distance from the center, and we'll see that this v theta is actually a function of r, or depends as power 1 of r, and in the case of free vortex is the inverse. Basically it depends as 1 by, it has a 1 by r dependence. Okay, so that's the basic difference between the definition of free vortex and forced vortex. I'll just write it. For free vortex, v theta is some constant c by r and vr is equal to 0, and you'll see that this c actually is the circulation. Okay, net circulation. The constant c is the circulation. And in both cases, for free and forced vortices, the radial component of velocity is 0. Okay, so let us try to and circulation, as I already mentioned, is defined as the line integral of v dot dl. Okay, so this was again thoroughly discussed by Prof. Chakraborty, so I'm not going to read again and again, but I'll just go to the example so that it clarifies the doubt. Okay, so circulation is defined as the line integral of v dot dl, and for the sake of simplicity, it is for this particular problem we saw that we can, instead of dealing with if you want to just see the see whether the circulation, net circulation is 0 or not, you will see that you can just do something like convert this into a surface integral, where using the Stokes theorem, so you can convert this line integral to a surface integral using Stokes theorem. So we will be dealing with integration of this form. Okay, so let me just use this one as this form, and this gives you net circulation. And since you will see that if you, just to tell you the answer for the first part, like if you do the cross product of nebula dot v, nebula cross v, you will see that this turns out to be non-zero. Okay, this will turn, it will be not equal to 0, and thus you can say that circulation is not non-zero, because since the integrand is non-zero, so our circulation will also be non-zero, and you will see that it eventually turns out to be 2 omega, and we will eventually find that. But to answer the first statement, that is whether the circulation is 0 or not, and since the vorticity is non-zero, so circulation will be not 0, so this is incorrect, as rightly mentioned by Saurabh. Okay, now let us try to just find it using this concept line integral. So if this is an elemental area where the circulation has to be found out, that was given in the question. Okay, this was the area at which you had to find out the circulation, that is through A, B, C and D, through this particular line. Then the basic exercise was to just to find the components of velocity along A, B, C, B, C, C, D and D A, and then find the integral of v dot dl. Okay, and see, it is easy because since the radial component velocity is 0, so the velocity at circulation along BC and AD would be equal to 0, which is shown here, and the only contribution would be because of the radial component of the tangential component of velocity along AB and CD. So along AB it is minus omega r dr, okay, and along CD, because if we take the sense of v theta as a counterclockwise direction, so and since we are taking the line integral along this direction and the velocity is along the counterclockwise direction, so the sense will be negative. Okay, so that's why it is minus omega omega into r d theta, where r d theta is the arc length. Okay. Similarly at CD, the velocity will also be omega into r plus dr, because the radial distance from the center is r plus this distance dr, and the arc length would be r plus dr into d theta, because the angular displacement remains the same, but the radial displacement has changed from r to r plus dr. Okay, and this will again be positive because velocity is taken along the counterclockwise direction, and the integration that we are taking at this point is again along the counterclockwise direction, so it will have the same sense, direction sense, so it will be positive. Okay, so once you deal with this integration, you will see that the circulation is let me go back, is v dot dl, and it will be the circulation along AB and CD and it turns out to be 2 omega r dr d theta. Okay, I'll show you how it came out. So circulation per unit area will be given by circulation by dA. So the dA is r dr theta, the elemental area is r dr d theta, and the net circulation is 2 omega r dr d theta. So once you calculate it, you will find that circulation per unit area is 2 omega. Okay, so it is non-zero. Basically gives us the vorticity, so it is non-zero. That's why the net circulation per unit area is non-zero for a forced vortex. Okay, and if you carry forward this calculation thoroughly, which I have done here, you will again see that this is the net contribution from circulation along AB and CD. So you need to expand it. So I've expanded it. So you'll see that the first two terms will cancel out, and you will be left with 2 omega r dr d theta and omega dr square d theta. And since dr is very small, then this contribution from this term will be very small, so it will basically tend to 0. That's why we will have gamma as 2 omega r dr t theta, which is something that we have shown here. Okay, so as Saurabh rightly pointed out, this is incorrect. Okay, and the radial component velocity is 0. This is again true, so this is not our option. But let us look into point C. There is a point of singularity in the case of tangential component velocity as the radius becomes 0. So we see that for forced vortices, if I go back, velocity components are defined as v theta is omega r and vr is 0. So at r equals 0, there is no singularity because this will just become 0. But in the case of free vortex, if you are having some r equals 0, this shows a point of singularity. Okay, so if that statement was for a free vortex, then at r equals 0 there is a singularity because this becomes undefined. But for a forced vortex at r equals 0, it's basically 0, so it is properly defined, so there is no singularity. Okay, so from this we can say that both of these statements B and C are incorrect. Okay, so is it clear? Can I proceed further?
Yes, sir.
Okay, thank you so much. So the second question is again statement type question, statement assertion type. The statements, the streamlines and equipotential lines may not be orthogonal at all points in the flow field. The streamlines and equipotential are not orthogonal at the stagnation points. So which of the following statements are correct? I think I just discussed it before we were discussing the Q&A part about the stagnation points and how the streamlines and equipotential lines are perpendicular except at the stagnation points. So I think I already told the answer, so this is the correct answer. Both statements are correct, and the second statement is the proper explanation for statement 1. Okay. Now question number 3 is if the curl of a vector is a null vector, then the vector cannot be presented as a gradient of a scalar function. Is it true or false? Basically saying that if del cross V is 0 vector, more correctly, then we cannot represent V as something like this. So it basically happens from vector identity that if this is the case, the curl of a gradient or divergence of a gradient is 0. Okay, so if it's something scalar function, this would be equal to 0. So with that idea, we can say write something like this. So they are saying that if del cross v is okay, Saurabh is saying false. So others, the question is if del cross v equal to 0, then we cannot write v as a gradient of a scalar function. So if you recall, it's something that we used to define the velocity potential. So can others also contribute? Is it true or false? Go back to the definition for the velocity potential. So there we see that how we take the aid of this vector identity to define the velocity potential. And I think it is something, it will give you the answer right away, whether you can represent v as a scalar function of gradient of a scalar function phi, which is the velocity potential. So it is okay. So it is indeed false, because if del cross v is 0, is basically a conservative field. In that case, we can represent v as a scalar gradient of some scalar function phi, where phi is the velocity potential. Okay. We indeed look into a detailed derivation of how we are able to conclude it, and again there is an inherent vector identity that supports this statement. So with those two things, I think you can support the claim of this, the validity of this particular statement. Okay. So let us go to question number 4. Again, for this, you need to take out your pen and paper. So to calculate, so the question is, let V be a two-dimensional steady state. Again, two-dimensional steady velocity vector field given by V is 2xi cap minus yj cap. Okay. The rate of angular deformation epsilon dot xy, the velocity of the fluid element, and the angular velocity omega z are given by. So need to evaluate both epsilon xy dot and omega z. Okay. So you can just go back to the expressions for epsilon xy dot and omega z and find, and given the velocity field, you need to tell me the values of epsilon xy dot and omega z. Okay. So I will give you 5 minutes. You can, it's a very simple calculation, but still you need to evaluate it. So you can just evaluate it and tell me which are the correct values of epsilon dot xy and omega z. So Saurabh says it's B. So others, can you tell? I'll wait for say till 7:20 for others to also contribute. Then I will proceed further. I need one more answer from one of you. Then I would like to proceed further. It's very simple. Epsilon xy dot would basically be half of dou u by dou y plus dou v by dou x. Both u and v you know, you need to find out that, and angular velocity would be half of dou u by dou y minus dou v by dou x, or it's just the other opposite sign, and you can see which is correct. Just substitute the value of u and v in those expressions and tell me what will be the correct answer. u here is 2x, v is minus 2y. So just substitute the value of u and v in these expressions and tell me the answer. Saurabh says it's B. So whether your answer is also the same or is something else. Okay, so time's up. So I really would have appreciated it if one of you have also contributed to the answer, but it's fine. Let us just see here. So if we do that, epsilon dot xy would be half of, then u is 2x, so dou u by dou y is 0 plus dou u by dou x v is 2y, so it's not a function of x, so it's again 0, so epsilon dot xy is 0. Similarly, omega z would again be the same because both v and v is not a function of y and v is not a function of x and u is not a function of y, so both of these would again be 0, so it will be 0. The correct answer is B. I hope it is clear, but I would have really appreciated if others would have also been contributed to this question. It's quite simple, but it's fine. Okay. Question number 5 is, which of the following statements is or are correct? Okay. So difference in the value of stream function between 2 points gives a quantitative idea of the mass flow rate across the line element that joins the 2 points per unit width. Okay, this is something that is related to the derivation taken by Prof. Chakraborty. So that I was basically discussing, that how there is no flow across a streamline. Okay. Statement B is the value of stream functions varies from one point to another along a streamline. See, sometimes in highly confined flow passages there can be a flow occurring across the streamlines, or D, none of this. So which of the following statements are correct? Is or are correct? Okay. So it's again simple theoretical question, something that I already discussed today again and again. So you can tell the answer. So I will give you 2 minutes. You can just go back to your notes and cross verify the statements. It's quite simple, we just discussed it when we're discussing about stream functions. Saurabh says it's A. Okay. I would again appreciate if others also contributed. It's ideally not good if only one student replies to all the questions. It's a good exercise or a good practice if others also contribute and make it a more interactive session rather than a monologue. But it's fine. It's not an issue, but I would appreciate it if other students also contributed to the discussion. It's quite mundane, but still it's a good practice and it's highly appreciated in the academic background if the class is made interactive from the student side as well. So okay, nevertheless it's actually correct. The correct statement is only option number A, because if we look, that is, the difference in the value of stream functions between 2 points gives a quantitative idea of the flow rate across the line element that joins 2 points per unit width. Okay, it's a long statement, but it's again basically being deduced from a simple expression that we discussed here. If I go back, that from this equation where we saw that q2 minus q1 over a particular width or per unit width is psi2 minus psi1. Basically the mass flow rate between the two stream functions is given by the difference in the value of the stream functions. Okay, so if there's a two lines of constant psi, basically I will just draw it here. So it is psi2, psi1 of say some constants c2 and c1. Then the mass flow rate through this particular, or the volume flow rate through this particular uh, region is given by q2 minus q1, or basically, or more preferably I could write something like q12 between these two regions per unit width is given by psi2 minus psi1. Okay, and you see that this value of this particular stream function is constant along a streamline. Okay, so this statement becomes incorrect. So this is incorrect, and the sorry, this is incorrect. There is a value of stream function varies from one point to another along a streamline. So value of the stream function remains constant along a streamline. That's a very fundamental statement. So this is incorrect. And in highly confined flow processes, there can be no flow across a streamline. So this is incorrect because this is again fundamentally negate the very definition of stream function. So that's why this is not possible. So the only correct statement is option number A. So for 5 is the option number A. Okay. Question number 6 is for a 2D incompressible rotation. Okay, again a strict condition. 2D incompressible irrotational flow, both stream function and velocity potential satisfy the Laplace equation. Again, it's quite simple. I just discussed it, so you can tell whether it's true or false. So saying that for this case, we will have Laplace equation del square phi equal to 0 and del square psi equal to 0. True. Okay, so it is correct. So I don't think I will wonder about this question for a long time. So it's quite simple. It was thoroughly discussed. So I think I can proceed further. But again, if you have any doubt, you can stop. But I would like to proceed further. Okay. Question number 7 is that statement, again statement assertion type question. A solid boundary is often considered as a streamline. Okay, that's the first statement. The value of stream function along the solid boundary must always be equal to 0. So again, a very specific scenario. The value of the stream function along the solid boundary must always be equal to 0. So which of the following statements, or which of the following options are correct? Both statements are individually true, but statement 2 is the correct explanation of statement 1. Both statements are individually true, but statement 2 is not the correct explanation of statement 1. Statement 1 is true, but statement 2 is false. Statement 1 is false, and statement 2 is true. A bit tricky. I will not say it's that simple, because intuition can give you a different idea, but in actuality the answer can be different. So you can take a bit more time to discuss about it. And it was discussed by, okay, Saurabh says it's D. Interesting. Others, can you say some option? I'll give you 2 minutes. So I think this was discussed by Professor Chakraborty, but I think when and moreover he also took an example where we needed to find the values of the stream function. Okay, there he told us how we can take the value of the stream function along a particular boundary, but whether or not it had to be 0 all the time, he didn't specifically mention, but he told that keeping the value of the stream function along a particular solid boundary as 0 is good because it gives a particular frame of reference. Okay, but it's not required that it has to be 0 all the time. Okay, but this statement 2 specifically mentions that it has to be 0. So that again is difficult. So again, so the thing would be that for a flow, say along a particular plate, flow over a plate or flow along a particular confinement, the solid boundaries are always treated as streamline because theoretically they satisfy the condition that there is no flow across them, so they act as a streamline. Okay, and flow velocity would be 0 along them because, and if you take the tangent along that, it will give 0 velocity because the flow velocity would be 0 at that particular boundary. Okay, so the thing is, this first statement is 0, because first, for the simplicity, these solid boundaries are always considered as streamline. But the statement 2 is incorrect, because even though it is preferred to have the solid boundary, the velocity function and the solid boundary to be 0, but it's not always necessary. Okay, it's a good approximation but not a generalized conclusion. Okay, so that's why statement 2 is incorrect, but statement 1 is correct. Okay, so the correct answer would be option C. Okay, Saurabh, is that clear? Okay, thanks, Saurabh. So the final question is again very simple. Velocity potential can exist for both rotational as well as irrotational flows, while stream function is only valid for 2D incommensurable flows. State true or false. Is velocity potential valid for rotational flow as well? Let me give you a hint. The second part is true. Stream function only valid for 2D incommensurable flow. But what about the first part? Is velocity potential valid for rotational flows as well? Yes, correct. So question number 8 here, the velocity potential is not valid for rotational flows. That's why this statement would be false. Okay. So I think that's all from my end today. So I think we can then meet in the next class. If you have any doubt in the questions, you can ask. Otherwise, we'll meet in the next class. Okay. Next class would be on Tuesday. So just to remind you, this Tuesday. Okay then, so if there's no doubt, then thank you everyone. So thank you for attending this session, and thank you for considering the shift in the postponing of the session and being so generous to attend in a sincerely attend the session complete for the entirety of this timeline, so time frame. So thank you for that. So let's all then again meet on Tuesday. Okay, thank you so much.